Sir, is it visible now? Hello. Okay. Okay. Thank you. Actually, sorry for this issue. And maybe as we joined little, we started this session little late. We can go with directly the slides and questions. Okay. So I welcome you again in this weekly live session, and this is our ninth live session for the course welding processes, right? And so far we have seen non-consumable welding processes and some variants of consumable welding processes like GMAW, FCAW, and SMAW. Okay, and in GTAW we have also seen the physics behind the arc, and uh, uh, there are different factors how they are actually contributing, and by manipulating the different current conditions or power sources, how we can uh, uh, generate different variants of GTAW. Okay, so also we have seen resistance spot welding, and we solved some numericals on resistance spot welding also, right? So in this live session we will start looking uh, the numerical of high power beam sources like power beam welding processes. Okay, and in this first set of question I actually added some questions which are actually related to the uh, heat affected zone and role of power high power density, right, or high energy density on the heat affected zone formation, right? So just for quickly recap, I just want to tell that uh, the whatever process we have seen in the GTAW and GMAW, they are low power density. They are using sources of low power density. Okay, and what it mean by actually low power? Low power is actually, we can say that the heat is actually concentrated on let's say, in other words, if we say there are two processes. Okay, or just for comparison, let's say if you consider arc welding operation, okay, and if you consider laser welding operation or electron beam welding operations, right? So if you remember, for melting that parent material, we have to give certain energy, and if the processes having using the source of low power energy density, then obviously heat input for this process will also be higher, and amount of heat which is actually transferred to the surrounding metal, uh, that will also high in such a cases, right? So always heat affected zone formation will be wider in case of the processes which is having low energy density. Okay, and this heat affected zone formation, or let's say in case of high power energy density processes like EBM, electron beam welding, or we can say laser beam welding. Okay, narrow, we can say it is narrow fusion zone, and we can say heat affected zone also. Okay, and here in case of arc welding processes or conventional welding processes, we are getting uh, uh, wider heat affected zone. Okay, and also we can say in case of energy density or power density for such a processes are actually in the range of 10 raised to, just a minute. Okay, 10 raised to 7 to 10 raised to 9, can say, watt per centimeter square. Okay, and in case of high energy or power density process, these values around, I think, 10 raised to 7 to 10 raised to can say 10 raised to 10 to 10 raised to 13 watt per centimeter square. Okay, I think it is 10 raised to 2 to 10 raised to 4, and here they are ending with 10 raised to 7 to 10 raised to 9. Okay, and as because of narrow fusion zone in case of high power energy density sources if we use, so heat affected zone is narrow, and also we can say distortion problem is less, right? Okay, and here distortion problem is more. Okay, okay, and another way we can also say that cycle time is higher here, cycle time or well time we can say longer, right? So that's why let's say uh, if we consider any heat affected zone in case of conventional arc welding processes, heat affected zone is the material which is actually surrounded to the fusion zone, okay, which is affected by the higher heat input, right? And what will happen because of that, we can see let's say if we consider any center zone, in the center zone we can add some external heterogeneous nucleate agent, right? Like let's say some particles which are stable in the molten metal also. So that particle we can add externally, and those particles can act as a nucleation sites. Okay, that means during the solidification of the weld zone, we can expect some heterogeneous nucleation and very finer grain size, right? But the region which are surrounded to the naked zone are actually only affected by the heat, right? There won't be external addition of the material will be there. Okay, so that's why the properties of this metal won't can't be modified later verse also, right? So that's why there always be in certain cases there always be the higher grain growth in the heat affected zone, and also it is actually unmodified. Okay, that's why in this most of the cases heat affected zone is weaker, and during the mechanical testing or mechanical servicing we can expect failure will be happening in the heat affected zone. Okay, uh, uh, and let's say the strength of the if the finer grain size if we able to achieve in the fusion zone, then we can say the strength will be more through this relation. Maybe you are aware about this, right? This Hall page equation. uh, so higher lower will be the grain size, higher will be the yield strength. Okay, but same case let's say in the laser beam or electron beam welding, uh, narrow zone is very fusion zone is very narrow, and heat affected zone is also narrow because heat is concentrated as we are using higher power density source. Heat is concentrated per unit area. That area will be very small. Okay, that means energy density will be higher, so that heat won't be transferred much to the surrounding area because of higher temperature gradient. Okay, uh, and also higher cooling rate can be achieved here. Okay, so in other words we can also say uh, uh, okay, in other words we can also say in certain cases if we consider the center zone. Okay, because of higher cooling rate, this center zone there are segregation of the intermetallic will be there at the center of the fusion zone, and that will cause a failure. Okay. And also there are other ways, other difficulties in case of laser beam weldings and or high energy power density processes are actually there is no escape of the gases, right? And those gases can be uh, 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 subjected to the right. So metal can be subjected to the uh, porosity or segregation issue, or that cannot be avoided, right? Or that can be avoided with the certain homogenization treatments. Okay. So in that way we can say that let's say if decrease the size of the weld pool and heat affected zone are observed during the welding while using, right? So as I said, weld pool is smaller, and also heat affected zone is narrow in case of laser beam and electron beam welding processes, because actually those processes are having higher energy density sources we can use, we have been using, and the actual heat input will be lower. Okay. So that's why we can say A option is more appropriate for the first question. Okay. And in the second question, with increase in power density of welding processes, time required for fusion. Okay. So this time required for fusion uh, is actually decreases because of heat is concentrated to very narrow area. Okay. In case of higher power density or processes, right? So with increase in power density, we can say time required to form the weld nugget or fusion zone is actually decreases. Okay. So in that way, first and second question we can answer, right? So okay. So we have also seen in the regular classes that the physics behind generation of the laser source for welding operation, right? So that also we can revise here. And in other way, let's say what I explained just now, I just want to add some more thing that as I said, if the thickness of material is higher, and then this distortion problem is more severe. Okay. And we can see even at higher thickness of the weld during the laser beam and electron beam welding processes, distortion problem won't be that much severe. Okay. And this distortion problem is higher in case of conventional the processes which involve the uh, arc, right? And also this distortion problem is even more severe, or a more wider heat affected zone is actually forming in case of gas welding operation, right? Because there we are actually using some kind of flame for melting the parent material, right? And then flame is quite wider, so that most of the base metal area is affected, or it is actually uh, come in contact with this flame. Okay. So again heat affected zone is more wider in case of gas welding operation. Okay. And due to temperature gradient, distortion problem will be there. Okay. And also we have seen that as heat input of the process increases, uh, tensile strength of the material will decrease. Let's say this is an example of particular aluminum alloys, and this tensile strength will be decreasing because of let's say all these are precipitate hardened alloys. Okay. So in the heat affected zone, the dissolution of the precipitate will be there. Okay. So it becomes and it becomes very weak during the mechanical testing. Okay. Or we can say in other words that let's say in the fusion zone of such alloys, the complete dissolution of the precipitate, strengthening precipitate will take place. Okay, and after the giving a proper heat treatment, post weld heat treatment, that precipitate can be renucleated in the fusion zone, and the strength of the weld can be increased. But again, heat affected in the heat affected zone, there is a partial dissolution of the precipitate, or sometimes we can say that those strengthening precipitate can be grow bigger. Okay, so because of that, if the precipitates coarsening will be there, then the material will lose its strength. Okay, that again, the material become weaker in the heat affected zone. Okay, so because of this problem in the precipitation hardenable aluminum alloys, by increasing the heat input, tensile strength of the material will decrease. Okay, and we have also seen that by increasing the energy density or power density, these processes are in the, arranged in the ascending order. So we can say by increasing power density here, for the processes which are actually using some high power energy source like a laser or electron beam, so power density of such processes are higher compared to conventional processes. Okay, so this is actually the basic that I want to revise here. And also in case of laser beam welding, we have seen some plots, like by increasing the let's say if we want to weld very thicker section, then we can use higher power beam sources, because we can able to get keyhole type of or through thickness of the weld. Okay, and as the only variables in such a processes are, we can say, travel speed. So the travel speed, if we have to weld thicker plates, then travel speed of the laser beam source will be less or smaller, so that we can ensure the through thickness penetration. Okay, so before going through these questions, we can again revise this basic, that in the laser beam welding, we can use different type of laser sources, like solid state laser, like neodymium doped yttrium aluminum garnet. Okay, and also gas type of laser. Okay, and also diode type of laser and fiber laser. Okay, so in the fiber laser, if you remember that the power density can achieve even very higher compared to other sources of laser. Okay, and we can see here, obviously this is not under in the range of visible spectrum. Okay, so we can't able to see the laser. Okay, and we can use that with the in the keyhole as well as conduction mode, that we can see in the subsequent slides. Okay, and if you remember, the basic principle in the laser is actually in the optically active material, we can say any optically active material, if we give certain amount of incident energy. Okay, that kind of maybe the any other laser source that can also be used here. So if it is actually striking, electron will go to the low energy to high energy state, or you can say excited state. Okay, and if we remove this incident energy, or if we stop the incident energy, we can say that the electrons from the higher energy level, that will again come back to lower energy level, or we can say in another way, electrons will comes from excited state to ground state. Okay, so as the energy of the electron will be releasing, because in the excited state energy of the electron is higher, so that excess energy that will come in the form of photon. Okay, and that photon actually so this is kind of continuous process, and these photons can be accumulated in one kind of coherent beam with the help of some reflecting mirrors. Okay, and to make this beam very coherent, and we can say coherent means high frequency or same frequency, and okay, and phase difference we can say. This coherent beam can be transferred from the any partially reflecting window. Okay, so this source is quite bigger, and in case of solid state laser, but in case of fiber laser, the sources is very laser source can in the form of optical fiber cable. Okay, so that is very flexible, and we can uh, uh, join any zigzag kind of welds also, and which is always having higher power density. Okay, so this is just basic regarding the laser welding processes, and also we have also seen in the slides from the regular lectures that in the laser welding processes we generally form tear drop kind of nugget. Okay, and as this is welding direction, the solidification will take place behind this source. Okay, or surrounding to nugget area, and this will be generally like a columnar type. Okay, so as I said, again, these kind of processes are very difficult to join certain material, like which are actually prone to the hot cracking or hot tearing, because maybe this kind of material will undergo solidification cracking because of higher cooling rate. So in during the solidification of the material, tensile stresses will be developed on the grain boundaries during the solidification, and due to constraint of the surrounding metal, uh, uh, the tearing of the grain boundary area will be happening. Okay, so that kind of hole cracking can be the problem in certain alloys. Okay, when the higher cooling rate will be provided. Okay, but we have also seen that in laser welding can be used in the different ways, that let's say if you want to do very thicker plate, then we can use the proper laser source and welding parameters, and we can ensure the through thickness, or in the keyhole mode of the welding we can do just like we can see here. Okay, but let's say in the other processes, the conventional processes like MIG, the efficiency of the welding processes are low, and heat power density is also low. Okay, but those processes are quite economical. So there are some attempts like the combination of laser plus MIG welding can give higher depth of penetration as well as some wider bed. Okay, so that load won't be concentrated on the very narrow area. Okay, and we can give a much more wider nugget area, as well as full penetration in such a cases of hybrid mode of welding. Okay, so that all those things we have already seen, so we can solve the question based on that. That as we have seen that NDAC laser is nothing but solid state laser. Okay, and the full form of this NDAC laser is we have seen that it is a neodymium dope yttrium aluminum garnet. Okay, so neodymium is actually doped in this thing to increase the life of the laser. Okay, laser source, and we have also seen that the wavelength of this NDAC laser it is in the range of 1065 nanometer to 1550 nanometer. Okay, so these are very basic questions, and also Okay. And also we have seen that by increasing the welding speed, size of the weld pool. So if we increase the welding speed, the time spent on the particular location by the source is or torch, or we can say, is very small. So if we increase the welding speed, obviously uh, uh, the nugget formation or nugget area will be smaller, and depth of penetration will also be decreasing, right? So as we can say, weld pool area will be decreasing, okay, by increasing the welding speed. So we can say here the welding speed, weld pool area decreases, and penetration also decreases. So C is the correct option for that. Okay. And they ask in the seventh question that which mode of laser beam welding is preferred to achieve increased depth of penetration. Okay. So maybe we will see that in the subsequent slides. There are different mode of laser beam welding or laser beam processes, like conduction mode and also keyhole mode. Okay. So in the conduction mode, we are just treating the surfaces with the help of laser beam, and we can deposit certain layer or different material, or we can say powder layer, by locally melting with the help of laser sources. That is, nowadays it is called as additive manufacturing. Okay. Or layer by layer additive manufacturing through the laser source. Okay. So also there are different treatments like surface hardening treatments, and even surface or machining of weld uh, machining of the plates can also be done with the help of laser source. So that kind of thing, maybe some numerical we can see on that topic, right? But just for through thickness, to ensure the full penetration, that mode of penetration is nothing but keyhole mode, we can say, right? And for eighth question, we can say that when the laser welding speed increases, depth of penetration generally decreases. So again, it is a repetition of the sixth question, but there is no exponential relation between that. Okay. So it simply decreases when we increase the laser welding speed, right? And also in the ninth question, they ask that shape of the weld pool during the high speed laser beam welding processes, as we have seen in the macro graph, that shape of the nugget or weld pool is like a teardrop shape, right? And also laser beam can be easily manipulated because of, so as we have seen, let's say conventional arc welding processes, there are different power sources. So each power source have different component, right? Like we can say diode, transformer, rectifier, we can say, right? So the and each devices have their own response time. Okay. So that may be higher, and means quick response times cannot be possible in the certain devices. Okay. That's why we can't simply stop and on the process in a very narrow time duration. Okay. And we have also seen that arc, though the arc is extinguishing, still some area or some kind of sparking we can able to see in such cases. So it is kind of inertia effect, right? So that inertia effect is not there in case of laser beam power sources, because in the laser can be quickly stop and start, right? So that inertia effect won't be there. Okay. So that's why we can easily move the torch if we want to do any zigzag or complicated type of weld. And also in the additive manufacturing, we can quickly rotate or move the laser with the certain angles, and we can even do the complicated geometry. We can do the deposition of complicated geometries, right? So as I said, the laser beam can be easily manipulated, because laser beam does not have any inertia, so it can be quickly start and stop, right? So laser beam does not have any inertia is the correct answer for 10th question. So I think with that I quickly go through the first set of question. So anything you want to discuss on this first 10th question, you just unmute and ask, right? No, not here actually, so we have not seen, but that can be used, like argon type of gas can be used here. Yeah. Yeah. Yes. No, so solidification traces are always generated during the solidification, but tensile traces are always be there during the solidification. But this kind of behavior will have been seen in certain materials only, which are actually having composition near to the rod composition. Like, just a minute. So it is not only restricted to the aluminum alloys. So any alloys which is having composition near to the eutectic point, so those alloys we consider as good for casting, right? So casting also involved again the melting and solidification. Okay, and we can pour the certain pour molten metal into certain pattern, and we can able to form the joint. Okay, but again here also solidification will happen. The alloy which is actually near to the eutectic composition. Okay, so in such alloys, let's say there are secondary phases that will form at much lower temperature than the its melting point. Okay, so there is very narrow difference between solidus and liquidus line. Okay, so this kind of composition really don't have any problem in such a case. But the alloys which are actually having rod composition, so there are any kind of alloy which is having a very wide solidification range, right? So in the wide solidification range, because of that, the solidified liquid won't allow uh, solidified region won't allow the liquid to go and add to the grain boundary areas. Okay, so there won't be sufficient liquid will there, right? Or there are certain continuous film of liquid can also be forming. Okay, so those alloys undergo solidification cracking compared to any eutectic composition. So that kind any kind of alloy which is having rod composition. So I hope it is clear. Okay. Okay. No, that is a different way actually. Any the material which is having good uh, absorptivity of laser, or they are bad reflector of the laser, that can be uh, the good for laser welding, right? So any, yeah, any bad reflector. So aluminum is a very uh, poor absorber of the laser, and it will reflect almost, I think, 90% of the incident energy. So we definitely can't use laser welding operation for joining of aluminum alloys. Yeah, but same way we can use that for other material which are having lower reflectivity. Yeah. It's depend on to what you are comparing. So question is related to what actually that we have to do. So easy to weld. So sometimes we, yeah. So any low conductivity material, that also we have to see. Like steel, any steel is there in the option, that also we can see, because steel have very low thermal conductivity compared to copper, and copper anyhow it is having higher thermal conductivity, so it is difficult to bend. Yeah. Yes. Okay. And also you ask about books, so I think maybe we can discuss that later, but I have been referring Robert Mesler and another books also for the cast for welding, like welding technology by Little and Palmer, that kind that some reference books are also there, but better to refer Robert Mesler. Yeah. Okay. So I think, so any other doubt, or we can simply go first? Okay. Okay. So another set of questions are actually related to the uh, what are the different forces which are actually again acting during the laser welding operation, right? So if you remember that professor explained, there are five type of forces we can say, like beam pressure or vacuum pressure, recoil pressure, and that has to be balanced by the gravity and surface tension. Okay. So left hand side the forces, like sorry, vapor pressure. Okay. So left hand side forces are actually aiding the keyhole formation, and they are actually right hand side forces are actually closing the keyhole. So we already saw this in during the arc welding processes, that liquid always have some certain surface tension value, and because of that liquid always try to contract its surface area, or it won't allow to change its surface area. So there always the surface tension force, or we can say pressure. Because of that the keyhole formation uh, is actually restricted. Okay. And also the gravity forces which are actually also try to closing the keyhole, because metal will fall again back to the like, let's say this is keyhole which is forming because of source. So because of gravity, metal the liquid metal which is actually here in this region, that will again try to fall back here. Okay. So gravity force and surface tension force, they are actually uh, closing try to close the keyhole, right? And other forces on the left hand side, like beam pressure, and this beam pressure, or this actually depending on the laser beam, we can say diameter. Okay. So higher the diameter, higher will be the beam pressure, we can say. Okay. And these vapor pressure forces are actually very important in case of laser welding process, because let's say this is keyhole which is actually forming here. So as in the laser we are giving sufficient heat, so material will undergo vaporization. Okay, and these vapors will try to uh, these vapors try to push this material outward. Okay, and in right, so because of that this keyhole is start expanding. Okay, so higher the beam pressure, it is actually supporting to the formation of the keyhole. Okay, and recoil pressure is also the vapors which are actually formed in the nugget zone or in the weld section. So those vapors are start try to escape from the escape to the atmosphere. Okay, try to escape. So if they are moving upwards, they will push the force downward. Okay, so that will again try to aid, or we can say form the keyhole or try to expand the keyhole because of their upward movement. So there are these three forces are actually very important for the keyhole formation, and maybe we can first solve the questions related to that. Then we'll go to the three different case studies what we have seen in the regular classes, right? So recoil pressure during the laser welding is actually created by, as I said, recoil pressure is because of the vapors which are which try to escape from the keyhole atmosphere or weld nugget. So recoil pressure during the weld pitch is created by vaporization of weld pool. Okay, so because of vaporization, these vapors are try to escaping from that to the atmosphere. So uh, uh, it will apply the rebound pressure on that. Okay, so it will aid the keyhole formation, or it will try to expand the keyhole. And also, which one of the following always aid the opening of keyhole? That we know that again the left hand side forces like recoil pressure, vapor pressure, and this one beam pressure are actually related to that, right? That will aid the keyhole formation. So travel speed is not actually the we can say force or variable in this, and it is related to this question. Okay, so C option is more appropriate. And for 13th question, we can say beam pressure in keyhole is depend on. So as I said, beam pressure will be depending on the beam diameter, uh, or we can also say in other words it's a spot size of the laser beam, right? So the higher will be the diameter, higher will be the spot size. So C option is the correct one. And in the 14th question, also we can say that closing of keyhole is depending on. So closing of keyhole is again it will depend, or there are two forces which are actually try to close the keyhole, like gravity force and surface tension force. But the keyhole at the bottom, keyhole means through holes we can say, but as torch move to further forward direction, because of surface tension of the liquid, this keyhole is actually closing up, right? So this closing up of keyhole is actually because of surface tension of the liquid, or we can say gravity also, but it's as it is a surface tension is there in option, so we can mark this option, right? And 15th question, they ask that vaporization of melt fluid creates the following forces. So we have already seen that it is related to vapor pressure or recoil pressure, right? So it is nothing related to the gravitation or beam pressure and Lorentz force. Okay, so for 15th question, A option is the correct one. Okay, so okay, So next set of questions are actually related to the case studies what we have seen in the regular lectures, right? So okay, so 16th question, we can say that formation of stable keyhole during the welding on galvanized steel in the lab configuration can be achieved by. Okay, so if you remember, we have seen there are three different cases. Okay, so let's say one plate, if we want to join two plates in the lab configuration. Okay, uh, uh, and in all the cases we can say there are similar thickness of the plates. Okay, and that plates we want to join through lab configuration, right? So as we have seen in the lab configuration, uh, let's say if you want to join the plates which don't have any coating, right? Zinc coating, or you can say galvanized coating. Oh, galvanized coating means zinc coating, you can say. So uh, uh, okay, that's the first case, that uh, there are two plates which are in the lab configuration which don't have any zinc coating. Okay, and in the second case, the plates will have again in the lab configuration with the same thickness, but there are there is a small or a thinner zinc coating will be there on the surface of the plates, right? That in the interface. Okay, so these are galvanized plate, we can say. Okay, so these plates okay, without coating, and in certain cases, let's say if we consider galvanized coating with let's say thin layer, here we can say thick layer around 20 micron, we can say. Okay, and here if you remember, there is no preset gap. Okay, so let's say keyhole, what we can able to see here is this one is your keyhole. Okay, so during the laser welding operation, vaporization of the material will take place in the naked zone. Okay, and if there is no preset gap and there is no coating, then again the keyhole which is actually steadily expanding, right? So the keyhole is forming, and once the pressure is sufficient, vapor pressure is built up in the uh, nugget zone, the keyhole is forming. Okay, and this pressure is constant, we can say, and there is a sufficient the vapors are actually escaping without any without any explosion, right? So spatter loss will always be less in such cases, right? So if we join without coating, but if we do the lab configuration laser welding of plates which are actually very thin galvanized layer, so this galvanized layer means we can say zinc. So zinc which is having very less vaporization point. So zinc vapor will form in the interfaces. Okay, and if there are no preset gap between the two plates, then this accumulation of these vapors will be there. Okay, and these vapors, as large number of vapors are there, that will increasing the pressure in the nugget zone. Okay, or in the center of the nugget zone. Okay, and that pressure is keeping on building up here, right? So because of that, there are certain values of pressure it will sustain, and after that the vapors has to escape from the escape to the surrounding because of high buildup of pressure. So it will escaping through the keyhole, and this keyhole is actually forming suddenly because of accumulation of the pressure, vapor pressure. Okay, so the keyhole size won't be uniform, and if the keyhole size is also not uniform, we can actually expect the sudden explosion during the escape of the vapors through the keyhole, right? So because of that, weld bed geometry as well as keyhole characteristics will be changing continuously, right? So it will again closes the keyhole once the pressure is releasing, and again the pressure will build up after the accumulation of the vapors, sufficient number of vapors. Okay, so the continuously keyhole characteristics are changing. That means again the weld form which is having variation in the size nugget area. Okay, so those properties are not good, right? So there are certain strategies professor discussed that we can maintain certain preset gap. Okay, in such cases, so that the vapors will escape through that preset gap. Okay, but again we have seen in the resistance welding also that if we maintain the preset gap between the plates, okay, if that gap is higher, okay, so this preset gap can act as a notch effect, right? And most of the cases intermetallics which are actually circulated at the center of this nugget zone, because of that notch effect, the strength will be uh, the stress will be acting at the center of the nugget zone, and it will fail through the center, right? Because of segregation of the elements. Okay, so this preset gap is in the thumb rule we can say it should be less than diameter of the laser. Okay, so it is not advisable in certain cases to maintain the preset gap. Okay, so in other way professor discussed that instead of using very thin galvanized coating, we can intentionally use the very thicker coating of zinc, right? And the plates thickness are same, geometries are same, like lab configuration. So the vapor pressure, because of higher thicker galvanized layer, amount of vapors which are generated during this in the center of this zone will always be higher, right? So as vapor number of vapors are higher, we can say vapor pressure is higher, so it will always try to open the keyhole, right? So keyhole is always open in such cases, though it is having larger size. Okay, that means the vapors are actually escaping continuously through that keyhole to the surrounding, right? So we can say in such cases it is possible that the keyhole characteristics are constant, or well bed area or nugget size will be constant. Okay, so because of constant keyhole characteristics, right? So by maintaining preset gap, or also we can have some intentional thicker coating of galvanized zinc, or we can say zinc coating. Because of that, large amount of pressure will be vapors will be generated, and subsequently vapor pressure buildup is always higher, so the keyhole is always be there, right? and vapors are always escaping from that keyhole, right? So these are the three case studies we have seen in the regular lectures that we can solve the question on that, right? So the formation of the stable keyhole during the welding on galvanized steel in the lab configuration can be achieved by, right? So this can be achieved by increasing the thickness of galvanized layer, right? So in the B option they said that maintaining zero preset gap. Okay, so if we maintain zero preset gap, then there won't be any space to escape the vapors, right? Metal vapors. So pressure will keep on accumulating there or increasing in the keyhole area. Okay, so it will again form the expansion or explosion of the center region, and because of that molten liquid will fall to the surrounding area and it will causes the spatter losses. Okay, so uh, by increasing the thickness of galvanized layer we can avoid that problem. Also we can maintain certain preset gap, so there won't be any zero preset gap. Okay, so welding in high pressure atmosphere, so this option can also be this is wrong in here, because if we do the welding process in the atmosphere with higher pressure in the atmosphere, then let's say in the underwater welding, then as because of higher pressure at outside, uh, uh, escaping of the vapors is difficult, right? So vapors are so in such cases we never end come up with the keyhole, right? So welding in high atmosphere pressure atmosphere is not again good for formation of the stable keyhole, right? So this option can also be ruled out. Okay, so A option is the correct one for 16th question. And for 17th question, while laser welding galvanized steel in overlap configuration without preset gap, the main force which control the keyhole stability is, right? So they said without preset gap, the main force which control the keyhole stability. Okay, so there is no preset gap, so vapor is not escaping. Okay, so obviously in such cases vapor pressure play the major role, right? Because vapors are still accumulating inside the nugget area and pressure will build up there. Okay, so in case of galvanized steel which is having zinc coating, which will easily vaporize, so the vapor pressure will build up. Okay, so vapor pressure will control the stability of the keyhole in such cases. And for 18th question, we can say which mode of laser beam welding is not preferred for laser cladding and deposition. So here it is, they are saying laser cladding and deposition, so it is a surface treatment. Okay, or so yeah, obviously it is not related to any overlap option. Overlap geometry can be used, and also keyhole geometry cannot be used here because we want only cladding, right? And bed on plate also not possible. So I think which mode of laser is not preferred for laser cladding and deposition. So obviously all three are not preferable, right? So the most preferable mode is here conduction mode. Okay, so all of the above is the answer. And for 19th question, laser welding of aluminum alloys is generally considered to be insufficient because of, or inefficient because of Again, as I said, aluminum alloys are good reflector of the photons. Okay, so we are using laser medium. Laser medium is what? It is a collimated beam of photons, right? So that photons will impinge on the certain material, and the kinetic energy of this photon will be converted into the heat energy, right? So if the any certain material which are actually poor absorber or good reflector of this photon, that cannot be heated up with the help of laser beam sources, right? So laser beam welding or laser welding of aluminum alloys is obviously inefficient, right? Because most of the photons will reflected back. Okay, so aluminum alloys are good reflector of photon, because of that it is inefficient. Okay, so as I said about here the conduction mode. So okay, so this conduction mode can also be using certain for certain heat treatment or flame hardening, we can say. So heat treatment or surface treatment of the material, right? Or any cladding or deposition of the certain material. Let's say we have any material substrate which is actually weaker, and if we want to increase its wear resistance, so we have to uh, uh, fill certain material, feed certain material like in the form of powder or any other foil, right? And if we use the laser source, that material of the top layer it's actually locally vaporizing or forming the melting area, and it will deposit on the substrate. Okay, so it is kind of surface cladding and a coating application. The laser can be used, and that kind of mode is nothing but conduction. Okay, so because here heat is only conducting at the surface of the plate. Okay, it is not forming any negate throughout the thickness of the plate, right? And also we can use, instead of welding, the laser source for uh, we can say cutting operation, right? So for cutting operation, like machining, we can say, if we want to form certain slot on the material in the particular area, maybe in the any form like zigzag way or any circular, non-circular, so anything can be possible through the laser cutting operation. Okay, laser melting operation. So it will locally vaporize the material into certain areas. Okay, and it will form the slot or any particular shape, right? So it can also be used as a slot making or cutting operation. So I think with that I try to cover all the questions related to the laser welding operation. And this is, I think, the doubt you asked, that the most preferable uh, we can say it is a dome or bell shaped electrode, but each electrode having uh, nature of the electrode is actually depending on the what kind of application we want to use. So let's say in the flat tip electrode, load is actually distributed in the case of resistance spot welding. So if the load is distributed, means what? We can say we can ensure wider bed, right? So if the load increases, uh, nugget size decreases, right? Because resistance will decrease, because it will squeeze out all the air, right? So resistance will decrease, we can say, and also the load will be distributed, so less melting, and we can say shallow penetration, or we can say wider weight. Okay, so that's why in the most of the cases actually truncated or 120 at 140 angle electrode is preferable. But certain cases, if the electrode having which are actually forming the localized brass layer on the surface of the tip. So brass having higher, you can say it is brittle layer, and its wear resistance is less. So because of that, this wear will it will wear out after certain time. So the shape of the electrode will change, and it will become at higher diameter. So higher diameter means what? Again, the weld bed penetration will decrease, and weld bed area will increase, right? So in that way we can use, but most of the cases for heavier load and severe heating, generally dome or ball shaped electrode can be preferable, right? So I think with that it is clear, because it is already written here. So any doubt on theoretical thing, sir, or shall we try to solve this numerical? It is one of the gate question. Okay, sir. Thank you. So okay, so I think it is question came, I think in the production or mechanical engineering gate exam, related to the laser cutting. So as I said, laser welding can also be, laser source can also be used for cutting of the blade, okay, or make slot making. So in such a numericals, as I said, simple thing we have to follow, that we have to use the efficiency concept. That efficiency is what? Output upon input. So what output we are getting and what input we are providing, right? So here obviously input is actually your laser power beam density, or laser power, right, whatever we are giving, and output is definitely uh, the how much heat actually we are actually utilizing there. So obviously, uh, in such a cases we have to compare input with output. Like if we multiply efficiency with the input, we are getting output, right? So let's say in this numerical, I will mark here. So they have 3 mm thick steel sheet kept at room temperature for 30 degrees Celsius, and it is cut by a fiber laser beam, okay, and laser spot diameter on the top surface of the sheet is 0.2 mm. So thickness of the plate is 3 mm. Laser power beam diameter is 0.2 mm, means we can say 0.2 into 10 raised to is 3 meter. Here also we can consider that kind of minus 3 meter, and okay, the laser spot diameter on top surface of the sheet is 0.2 mm. Laser absorbivity of the sheet is 50%. The properties of the steel, right? Absorbivity we can consider here. Let's say A is 0.50%, and density of the steel is I think 8,000 kg per meter cube. Okay, and the properties of steel, they gave specific heat, melting temperature, and latent heat of fusion. So specific heat 500 joule per kg, melting temperature 15, just a minute. Surrounding temperature is your 30 and melting temperature is your 15, 30. Okay, specific heat and latent heat they gave. So specific heat of the material is 500 joule per kg per degree Celsius, and latent heat they mention is 3 into 10 raised to 5 joule per kg. So power input of the process is 2 kilowatt laser power, and they said 100% efficiency. Okay, so and also they ask that what is the maximum welding speed we can achieve in meter per second, and they said that we have to round up the answer in 3 decimal spaces, and uh, width width is equal to the laser spot diameter. And they said that sheet can be fully cut, right? So and they said that width of the slot is actually equal to the diameter of the laser, and they ask about welding speed in meter per second. Okay, so again concept is same, that let's say if we have any rectangular plate, okay, which is having 3 mm thickness, okay, and they ask that uh, okay, this much area we have to cut, and I think okay, and I guess they gave that width of this zone is nothing but diameter. That means it is circular, and we can say certain area like width multiplied by thickness of the plate, so that much area we have to melt, right? And also uh, uh, we have the equation that let's say input equal to output, and they gave 2 kilowatt power, so obviously 10 raised to 3 we have to multiply with reflector efficiency or absorber efficiency, right? So this much of input power, but out of that only 50% are actually absorbing by the steel surface, right? So 50% is going waste, so we have to multiply that with the input power, right? And so here it is like kilowatt means what, kilojoule per second or joule per second, because here we are multiplying with 10 raised to 3. Okay, so LHS is unit is your joule per second. Okay, so obviously if we have to melt this much area we have to consider. Okay, and density of that material that we have to consider, right? And also welding speed. Okay, so because higher the welding speed, lower will be the melting area, that how we have seen, right? So uh, Okay, so I think, yeah, so for melting that much area, obviously we have to consider specific heat of that material and its latent heat, right? So specific heat plus latent heat multiplied by how much mass we have to melt. Okay, and mass is equal to, or we can say density equal to mass by volume. Okay, so obviously mass here is rho into V. Okay, so this rho into this one is your V, not V, it's a volume flow rate. Okay, or volume amount of material which is actually melting per second, right? Because here speed is involved, right? So this much multiply by mass with the help of means instead of mass we have to use these three terms and these three terms, right? So in other ways we can write rho area is your 0.3 multiplied by thickness of the plate multiplied by 10 raised to minus 3 and 10 raised to minus 3, right? And Cp of the material they already gave, like uh, 5 into 10 raised to 5. Okay, and Cp delta T is your sensible heat, right? So delta T is nothing but 1500, difference between surrounding and melting temperature of that alloy, plus latent heat they gave as 3 into 10 raised to 5, 8000. Cp is your 500. So Cp is your 500 and latent heat is 3 into 10 raised to 5. Okay, and this one is 8000. Okay, so now and multiply by welding speed, that is in meter per second. Here we converted all the entities in SI unit in meter, like 10 raised to this thickness, and also we know here these are the values in kilojoule per kg degree Celsius. Okay, so this one is joule per kg. Okay, so joule per kg we can say here, and this is your kg per meter cube, right? So kg got cancelled, and meter cube means here meter square, and this meter per second nothing but meter cube. So meter cube get cancelled, and this one is per second we can say. So all the unit got match, and if we compare that with these input values like 2 kilowatt into 10 raised to 3 into 0.5, so we can get welding speed in the range of, I think, 0.193 to 0.2. meter per second. Okay, so concept is same what we have seen in the resistance spot welding, and this type of numerical one can expect on the laser welding and laser machining operation, right? So I think with that I end up all the topics what I want to cover in this live session. So if you have any doubt, then we can again discuss, right? So with that, the numerical is clear, sir? Or Prakash? Okay, thank you. So anything again you want to discuss in this live session? Okay, maybe we can cover that topic what you said regarding solidification cracking probably in the last live session, that we will discuss that again in more detail, that what are the different regions. That's the only one region what I said about wrought alloy, but there are different regions like there are low melting eutectic phases which are actually present on the grain boundary area, and those phases are actually uh, uh, melting during the in heat affected zone, that will also cause liquefaction cracking. So those things maybe we can again discuss in the last live session in more detail. Okay. So if we have any uh, thing to discuss, then maybe we can free to discuss, or we can. I will be here up to 7 o'clock. Yeah. Yes. Yeah, we can discuss seventh. But you remember any question? Okay. Yeah. Okay. Yeah. Okay. Okay. Yeah. 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 I. Yeah. Actually, yeah, I solved that numerical by two ways, like by using simple equation like VI divided by welding speed. So that's the conventional equation that we have seen in the MMAW. But problem is they already mentioned about the length of the weld also, right? So that that equation we can't use, right, on that particular time. So and already they gave welding speed. So on the basis of that, we can calculate this uh, length of weld divided by, or welding speed equal to length of weld divided by time, right? So in that way we calculated the time, because they gave length of the weld bed. So that's why I didn't use VI by welding speed, that formula. Yeah. So and I okay. Oh, actually this yeah, 1,000 just yeah. No, I might divide it by 60 because time we need in the second, and if welding speed we can able to get in minute, then we have to divide that with the 60, right? Yeah, because of that I divided 60. Yeah, because they gave length like 900 mm, and time also they give, right? Time we have to calculate, so that's why I maybe multiply that with 1,000 or 60, but maybe, yeah, I have to check again. Yeah. So you want me to prepare for some more numericals on these topics, or this much is fine? Okay. Okay. Okay then. Yeah. Yeah. Okay, sir. Maybe then, uh, okay, we will try to cover, I think, welding length and power sources numerical in the last session, along with this, because last session is just simple welding of plastic material like polymer and all. So that we will finish that in half an hour. So we can discuss rest of time regarding welding metallurgy and some numericals based on uh, power sources. That power sources numericals are also very important. Yeah. So this that only is pending, and almost other all the type of numerical we almost covered, like mostly on the welding topics, right? So I will try to search for some more types. Most of the cases only volume is important, because that how we have to manage that volume calculations, because volume is the because certain time they already gave volume or energy in the joule per mm cube or joule per meter cube, like melt energy. So that where we have to multiply that with the volume, but in certain cases they will give cross section area, and we don't know the thickness, but welding speed is also one of the variable, just like in this numerical, and its unit is mm per second. So if we multiply that with the area, then we will get, because welding speed is what distance per unit time. So it is again that one particular length also we have been considering there. So that's why welding speed multiplied by area can also be considered as a the volume of the metal, which is actually melting with the help of certain input energy. So that is more important only, and also there uh, different formulas that we have to consider, like sometime it will form cylindrical melting volume, sometime it will form spherical in case of resistance part welding. But yeah, so I think that how we have to consider that there are nothing other things in this email. Yeah. So okay, sir. So if you don't have any doubt, then maybe we can close this session. I will be here up to 7. We can discuss all if you have any doubt. Yeah. Okay. Thank you. Thank you for joining. Yeah.